Before I begin, I'll just give a quick rundown of the contents. So I'll have a little section at the start, which is just going to talk about measurement, why it's important, how good measurement practice is encouraged in the United Kingdom. I'll then talk about custody transfer. So what do we mean by custody transfer? Some of the key sort of terminology that's important to understand when you're talking about custody transfer metering, things like uncertainty, turndown, etc. I'll then move on to different metering types and technologies that are commonly used in custody transfer applications. So, how do they work? What are the pros and cons of each? I'll then have a section on meter proving and fluid sampling and other, you know, important activities involved in custody transfer metering. And then I'll finish with a section on secondary instrumentation, so things like temperature, pressure, density measurement, and flow computers, and the role these all play in custody transfer metering. So just a few slides on the importance of correct measurement. Why is measurement important? Well, if you take the United Kingdom, each year approximately £622 billion worth of goods and utilities are sold on the basis of their measurement quantity. So there's a lot of money riding on good quality measurement. Now, how is good measurement practice and measurement traceability delivered in the United Kingdom? Well, it's through the National Measurement System. So this is a collection of institutes, and their primary role is to maintain the UK's measurement traceability chain. So NEL in particular is the designated institute for flow and liquid metrology. So we are responsible for providing the UK with physical flow and density measurement standards. So in addition to providing that traceability, we also help develop documentary standards. We enable industry through knowledge transfer, so activities like this webinar, and encourage best practice. And obviously, we're involved in metrology research, with the ultimate goal of providing value to industry. So, why would you measure in addition to sort of fiscal reasons? So obviously you've got custody transfer where you've got product changing hands. You need to know the quantities of the product that's involved in that trade, but there's several other reasons why you might want to measure things. So things like reservoir management, process control. If you're not measuring things like temperatures, pressures, flow rates, these activities are obviously going to be very difficult or next to impossible. Things like allocation, where you've got shared pipelines, you need to know how much you're putting into the shared pipeline and how much is getting taken out at the end. Things like environmental reporting. So if you're, producing water when you're obviously producing oil and gas and you're injecting it back into the ocean, you need to know how much you're injecting back in. If you're flaring gas, you need to know how much gas you're flaring. You can only do that through measurement. So there's not just monetary reasons. There's also several other good reasons why you want to measure things and you want to measure things correctly. So I'm now going to move on to the main sort of section of the presentation, custody transfer metering. So it's good to start off with a definition of custody transfer. So it's the transfer of ownership of assets. The focus of this presentation is obviously hydrocarbons from one company to another. So when we talk about custody transfer metering, it's the point where the fluid has been measured for sale from one party to another. So the metering or the flow meters act as the cash register, essentially. Now, it goes without saying that accuracy is of great importance to both the company delivering the material and the eventual recipient, and trust and transparency is vital. And the best way of ensuring accuracy, trust, and transparency is through good measurement practice. There's a few kind of key terminology or terms that is good to have a clear understanding of when it comes to custody transfer metering. One of them is turndown ratio. So what is turndown ratio? It's simply the ratio of the max flow to the minimum flow in your effective range. So this is a really important performance indicator. It will govern the design of a custody transfer system. It will govern the selection of an appropriate metering technology. So it's quite an important term. Next couple of concepts are gross observed volume and gross standard volume. So gross observed volume is the total volume of petroleum, liquids, sediment and water at an observed temperature and pressure. A gross standard volume is the total volume of petroleum, sediment and water at a standard temperature and pressure. Now, what's the key difference? Well, a custody transfer metering system, you're usually measuring or metering actual volumes or gross observed volumes. When it comes to custody transfer, when you're trading product, let's say, people tend to work with gross standard volume. It makes things much easier when you compare things at a standard temperature and pressure. Now, what's important whenever you state a gross standard volume, you need to be clear on what your standard conditions are. So typically, when it comes to oil and gas, it's 15 degrees Celsius and 1.01325 bar. Now, I say typically because people have different definitions of what standard conditions are, so it's really important to state what you're using to convert to gross standard volumes. It's also important to contrast this to net standard volume. So again, that's similar, but it's excluding the sediment and water because ultimately no one wants to pay for seawater and sand. And what's critical in terms of calculating net standard volume is sampling. So I'm going to talk about sampling later in the webinar. Another important parameter is uncertainty, and this kind of underpins everything in custody transfer metering. So what is uncertainty? It's a range of numbers either side of the measurement result within which we expect the true value to lie with a given confidence. So whenever you take a measurement, whatever technology you're using, the true value is going to lie somewhere either side of that measured value. So uncertainty quantifies the range of numbers within which the true value lies. The confidence is basically the likelihood that the true value will lie within that uncertainty range. So whenever you see a measurement result stated, it needs to have the measured value, it needs to have the uncertainty, and it needs to have the confidence factor. It's important again to make the distinction between accuracy and uncertainty. Accuracy is a qualitative term, so you can't assign a value to accuracy. The two are often confused, however, but if you want to quantify things, you really need to state an uncertainty. Now, for custody transfer metering, the following uncertainty limits are typical, and they're typically quoted at a 95% confidence level. So for liquid systems, it's plus or minus 0.25%, and for gas, it's 1%. So these are the typical kind of expectations for custody transfer metering. Again, it depends on the particular agreements between the parties involved in the custody transfer. There might be occasions where these targets are different, but generally speaking, 0.25% for liquid systems and 1% for gas. And these are quoted at 95% confidence, so if you took, say, 20 repeated measurements, you would expect 19 times out of 20, it would lie within your uncertainty band. So as I said before, uncertainty underpins everything in custody transfer metering. And some of you might ask, well, what's the importance of uncertainty? If we take an example of oil production, in 2022, there was approximately 100 million barrels of oil produced per day. At a $100 per barrel average spot price, that's approximately 10 billion US dollars per day. Now, if you have an uncertainty of 0.25, so plus or minus 0.25, your financial exposure is approximately 25 million per day. So the value can vary plus or minus $25 million. So that's not an insignificant amount. So the reason you've got uncertainty targets is it's to limit this financial exposure. So that's the financial exposure at 0.25%. You can imagine if you've got poor measurement quality and your uncertainties, double that or triple that, the financial exposure just increases. So it's suits all parties to target as low an uncertainty as possible when you're doing custody transfer metering. So, if you want to achieve a low uncertainty, it's not enough to simply place a flow meter in a line. Other components are required in order to meet those uncertainty targets. So, typical components in a custody transfer system obviously include flow measurement, but you've also got things like temperature and pressure measurement, which are critical for things like determining fluid properties. Density measurement is also important, depending on the metering technology that you're using. Meter provers are quite important to verify the performance of your flow measurement system. You've got sampling, where you need to obviously determine the quality of the product that's changing hands. Flow conditioners, again, depending on the flow measurement technology, these can be quite an important component. And flow computers, which collect all the various signals and measurements from all these different devices, perform calculations, might convert to standard volumes for you. Again, these are a really important part as well. So this is just an example of a typical oil export metering package. So it's a 4-stream system. So each stream here has a flow measurement device. In this case, it's a turbine meter. Each has got a pressure and temperature measurement. Each has got a flow conditioner, which is quite important in most cases for turbine meters. There's a prover loop, which you can periodically use to verify the performance of the turbine meters, determine things like meter factors. Each stream has a flow computer, or there might be one flow computer for all the streams, and that will be collecting things like the pulse train from the flow meter, the raw temperatures and pressures. It might take in composition measurement from your gas chromatograph, values from your densitometer, and ultimately will produce things like gross standard volume for you. And there's also a densitometer and a sampling fast loop, where you can obviously quickly take a sample from your flow stream. Now, obviously, this is a multi-stream system. So we talked about turndown. So turndown usually governs how many streams you've got. Now, it's often quite difficult to get a single flow meter to meter both the min and the max flow to the uncertainty. So your system up and wrap the meters together in parallel, and that allows you to maintain the accuracy that you require. But when you're metering small flow rates, you can turn off maybe 1 or 2 streams, and you can still maintain that accuracy and maintain those uncertainty targets. So now I'm going to talk about metering types. So obviously the metering technology that you select is one of, if not the most important aspect of a custody transfer system. Now there's several different metering types used in custody transfer metering. People tend to group them into sort of traditional and more modern technologies. So orifice plates, turbine meters, positive displacement meters, these are thought of as the more sort of traditional flow measurement technologies. Ultrasonic and Coriolis meters, they're thought of as more modern technologies, although they've been in use for a number of years now, and they're becoming, quite mature in their own way as well. So I'm going to talk about each of these and some of the sort of pros and cons. So orifice meters are extremely common. They're actually the most common type of differential pressure meter. So it's estimated that around 40% of industrial flow meters are differential pressure meters, and a large majority of those are orifice plates. So how does an orifice plate work? Well, it's quite a simple thing. It's a machined plate held between 2 pipes. The plate's got a hole in the center that creates a restriction in the flow. So as the flow goes through the restriction, the velocity increases, and as a result, the static pressure drops. So by measuring that pressure drop of the differential pressure, you can determine the flow rate, because the flow rate is proportional to the square root of the differential pressure. So you measure the differential pressure, and along with the fluid density, the area, and the discharge coefficient, which is the ratio of the actual flow rate to the ideal value through an orifice. This accounts for frictional effects. So if you've got all those things, you can determine the mass flow rate through the orifice. And they're quite a simple design, and they're suitable for both gas and liquid flow. So they're quite versatile. So why are these so ubiquitous? Why are they so popular? Well, obviously they're relatively simple and low cost. So there's no moving parts, so there's less maintenance required. They're easy to install, but you do need to take care that you install them the right way around. So orifice plates do have a flow direction. There's usually a sharp edge and a bevel. The sharp edge needs to face the incoming flow, because we've had sort of consultancy projects where we've audited flow measurement systems, and it turns out the orifice plate's been installed the wrong way around, which does lead to significant mismeasurement. One of the biggest advantages is there's comprehensive standards available. So ISO 5167 is a really mature standard. So in terms of calculating the discharge coefficient, you can use the ISO standard. A big advantage is if you manufacture the plate to the tolerance of the standard, you can use it without calibration. So these are very popular for gas systems. Some of the downsides are, obviously by their nature, they're creating a restriction in the flow. So there is a pressure drop, and depending on the flow rate, they can induce quite a high pressure loss in the line. So that needs to be considered. They've got a relatively low turn down. So typically sort of 3:1 to 5:1 is the turn down you can expect. You can increase the turn down by utilizing more than one differential pressure measurement device. Typically the limitation is the range of differential pressures you can measure. But if you have a bank of differential pressure transmitters that measure sort of a low, medium and high range, you can increase the sort of turn down maybe up to 10:1. And another disadvantage is they're very sensitive to upstream installation effects. So if you don't have a nice, fully developed flow profile going into the meter, let's say you've got swirl from bends or a partially closed valve, that's going to affect the meter performance. The next traditional technology is turbine meters. So how do these work? Well, you've got a free rotating rotor with flow in the pipe. The rotor usually has multiple blades, and the rotation of this rotor is driven by the flow of your fluid. And the flow rate is proportional to the rotor speed. So simply count the rotations and you can determine the total volume that's passed through the meter. So typically there's a magnetic pickup. Every time a blade passes the pickup, a pulse is generated. And what you do is you count the number of pulses, and that tells you the total volume that's passed through the meter if you use it with a K factor or a meter factor. So these are a well-established flow measurement technology, and they have a number of advantages. They tend to have very good repeatability. They're versatile in the sense you get designs for gas or liquid. Now, unlike an orifice plate, it's a different design for gas or liquid, so you can't use a gas turbine meter with liquid. It's usually one or the other, but the technology is suitable for gas or liquid. They're easy to install. Typically, it's just a flange piece of pipe, and they're relatively average cost, so they're going to be slightly more expensive than an orifice plate system, but they're not as expensive as some of the modern technologies that I'm going to talk about. Downsides are you've got a moving part, so they're susceptible to mechanical damage. Again, they're also sensitive to installation effects, so for these to work optimally, they need a nice, fully developed flow profile. And things like bearing wear can affect the ability of the rotor to spin, and they can become blocked by contaminants over time as well. So the next sort of mod or traditional technology is positive displacement. And how do these work? Well, they allow fluid to enter the meter, and they capture a fixed volume of that fluid. Once they've captured that volume, they then discharge that volume out to the flow. So it's quite simply count the number of volumes that pass through the meter, that gives you the total volume. So it's like repeatedly filling a bucket to a fixed level. You time the rate at which the bucket's being filled. Total number of buckets gives you the total volume. Now, because this is like a direct measure of flow, you're directly capturing a fixed volume. They tend to be very fast responding meters. They are accurate and they can be very repeatable depending on their design. One of the biggest advantages is they're insensitive to installation effects. So orifice plates, turbine meters, you need a nice fully developed flow profile. Usually means you need a certain amount of straight pipe or a flow conditioner. Positive displacement meters don't require that. So if you know you've got significant installation effects, positive displacement meters are a good choice. And they've been used as master meters to verify other flow measurement technologies. Downsides are they're susceptible to mechanical damage, again, moving parts, tend to be quite bulky and complicated devices, and they can be expensive as well. I'm going to move on to some of the more modern technologies, although they've been around for a number of years now. And the first one is ultrasonic meters. There's different types of ultrasonic meter. I'm going to focus on transit time meters because they're typically the most common. So how does an ultrasonic meter work? Well, you've got a pair of transducers, and what they do is they measure the transit time of ultrasound from one transducer to the other. So the speed of the ultrasound is dependent on the speed of the fluid which it's traveling across. Now, the transit time is measured both going with the flow and going against the flow. A good analogy is like a boat traveling with or against the current. If a boat's traveling with current, it's going to travel faster than against the current. And by comparing the travel time of the ultrasound going with and against the flow, you can determine the velocity of the fluid because it's directly proportional to that. Now the image shown here is a single path device, so there's one path being cut across the flow stream. Typically in custody transfer applications, you'd use a multi-path device. Now why is it important to use a multi-path device? Well, if you took a cross section through your pipe and looked at the velocity profile of your flow, it's not going to be uniform. So in order to determine an accurate average velocity profile, you usually need to use more than one path. So the more paths you use, the more accurate the meter tends to be. A good thing about multi-path devices as well is they have built-in redundancy. So if a pair of transducer fails, you've still got other pairs that can perform the measurement. So why are ultrasonic meters popular for custody transfer applications? Well, they're non-intrusive and non-invasive, so they're not typically going to introduce a pressure drop in the pipeline, and you can even get clamp-on ultrasonic meters that clamp onto the outside of the pipe. Now, these typically won't have the uncertainty you're looking for maybe custody transfer, but they're very good diagnostic tools. So if you have a system where it's you can't break the line and install a flow meter, you can use a clamp-on ultrasonic meter for those cases. They don't have any moving parts, so they're less susceptible to mechanical damage. They can give you diagnostic and secondary measurements. So ultrasonic meters can now tell you things about the profile of your flow. Have you got swirl within the flow stream? The speed of the propagation of the ultrasound is dependent on things like the composition of the fluid. So some can now indicate things like the density of the fluid. They typically have quite a low uncertainty, so 0.1% or even better, depending on how you calibrate them, and they have a large turndown. Now, turndown varies depending on which manufacturer you speak to. Some will claim sort of thousands to one turndown, but typically they have a larger turndown than the more traditional measurement technologies. Now, what are the downsides to ultrasonic meters? Well, typically they're quite expensive devices, and they can, again, like orifice plates and turbine meters, they're susceptible to installation effects. So again, for these to work optimally, they require nice, fully developed flow, although some multi-path devices can now sort of compensate for distortion in the flow stream. And the transducer ports, you can get deposition in them that can affect their ability to send and receive the ultrasound. But they are quite flexible, and they're available in quite small and quite large pipe diameters. So you can get up to sort of 48-inch size ultrasonic meters, right down to very small bore as well. So the last metering technology I'm going to talk about are Coriolis meters, and again, these are an extremely popular device these days, and there's a number of key reasons why they're so popular. Particularly, NAL, we calibrate a lot of flow meters. The vast majority are now Coriolis meters. So why are they, so popular? Well, the first advantage is they can give you a measure of fluid density. So how do they measure density? Well, typically a Coriolis meter will have one or two flow tubes, and these tubes are vibrated at a natural frequency. And by measuring the frequency, you can then determine the fluid density, because the frequency depends on the mass of the tubes, and when the mass of the density of the fluid changes, the total mass contained within the tubes changes. So, first big advantage, they give you a measure of fluid density. When you've got flow going through the Coriolis meter, flow causes the measuring tubes to twist. Now, this twist causes a phase difference between the inlet and the outlet sensor. So if you don't have any flow, you shouldn't have any twist, you shouldn't have any phase difference, so the phase shift should be zero. So when you've got flow, and if you measure this phase difference, the difference is proportional to the mass flow of the fluid. Now that's the big advantage of this meter. It will measure mass flow rate, whereas previous technologies typically are volumetric or velocity-based devices. They'll need other measurements like a densitometer in order to give you the mass flow rate of the fluid, whereas Coriolis meters can give you that directly. So what are the advantages of a Coriolis meter? Well, like I say, they give you multiple outputs, mass flow and density. So mass flow is a big advantage. It can negate the necessity for things like a separate densitometer. They are not susceptible to installation effects. So again, if you know that you're going to have installation effects like bends, T-pieces, valves upstream of the flow measurement device, the Coriolis meter is less affected than turbine meters, orifice plates, for example. And they also tend to be fairly accurate and have a high turndown. So they've got a higher turndown typically than the traditional technologies, and you can get uncertainty as low as 0.1% or better. Again, it depends on the calibration route and things like that. Now, obviously, they've got a number of advantages. What are the disadvantages? Well, zero stability can have an impact. So when there's no flow going through a Coriolis meter, the meter should indicate zero under ideal conditions, but in reality, small changes in temperature, pressure, vibration, ambient effects will result in the meter indicating a flow when there is no flow. So obviously, to account for that, you need to zero the device. But over time, the zero can drift, and depending on the flow rate you're trying to measure, it can have quite a big impact. Another sort of disadvantage is Coriolis meters have a well-documented pressure effect. So when the pressure of your fluid changes, that affects the stiffness of the measuring tubes, and that's going to affect how they twist when you've got flow going through the meter. So you need to account for that because the effect can be quite significant. Now, the good thing is the effect is fairly linear, so you can correct for it, or even better, if you calibrate at your operating conditions. So at NEL, we've got our elevated pressure and temperature facility. Primarily, this was designed to calibrate Coriolis meters at service conditions, so you can calibrate out the pressure effect, but it does have to be considered. In terms of the size of Coriolis meters, they tend to be limited compared to other technologies. So, typically 10, 12 inch is the maximum size. You do get up to sort of 16-inch flanges now, but as you go up in size with Coriolis meters, the costs do increase significantly. So, and another disadvantage is they'll introduce a pressure drop in the line. Now, depending on the flow rate, that can be quite significant. So Coriolis meters typically will have higher capital costs up front than some of the other technologies, but again, they've got numerous advantages, so you need to balance that out. In the long run, they might actually work out more cost effective than one of the more traditional flow measurement technologies. I'm just going to finish the metering section on flow conditioners. So we've talked about various technologies that require a nice fully developed flow. Now, the best way to achieve that is to provide long straight lengths of pipe. This allows any effects like swirl to dissipate before it gets to the flow measurement device. Now, what if you don't have the luxury of that, or if you've got limited space? Well, you can shortcut your way to fully developed flow using a flow computer. So these essentially help reduce installation effects, and you get various different types, including tube bundles, which is kind of the image shown here. You get perforated plates, honeycomb structures. They're all doing the same thing, but the key thing to obviously note is they will introduce a pressure drop into the flow stream. And if that's a big consideration, you might then want to select a technology like Coriolis or positive displacement, which is not affected by installation effects. So again, it depends on the metering technology if you need to implement a flow conditioner. So I'm now going to move on to meter proving and fluid sampling. So these are again quite important activities when it comes to custody transfer metering. So obviously, if you've selected a meter and you're using it to meter your flow, that's fair enough. But how do you verify the performance of the device? Well, obviously you can calibrate it at a laboratory, but that requires removing the meter, and in some cases that's not practical or achievable. So that's where meter proving comes into the fold, and it's similar to calibration, but it's usually performed on site and usually more frequently. So it is essentially a calibration, but it's usually done on site. Provers are often included as part of liquid metering systems, and what is a prover doing, or what are you doing when you prove a meter? You're comparing your meter's registered throughput to a known reference volume. Now there's various different types, designs and styles of prover. You've got pipe provers, you've got tank provers, you've got compact provers, which are another form of either a pipe or a tank prover, and you've got master meters. I'm not going to focus on every single different type of prover, but I'm going to talk about a few of them in the next few slides. So what's involved in a typical prover operation? Well, you've got the meter or your duty meter that you want to verify the performance. So you run the meter in series with the prover. Typically, the prover will have a volume that's been calibrated to a low uncertainty, and the volume is held between detector switches. And you're basically comparing the meter volume to the prover volume. And what you're doing is you're counting, if it's a pulse device, you're counting the pulses between the detector switches. Total pulses gives you an indication of the total volume from the meter. Compare that to the actual calibrated volume in the prover, and you can work out a meter factor, which you then might program into your flow computer to correct the output of your flow measurement device. Typically, when you prove a meter, it needs to be proved on a number of consecutive runs, and you need the reason for consecutive runs is to show repeatability below a given tolerance. Maintenance of a prover is obviously important because you're relying on the calibrated volume in the prover, you're relying on things triggering the detector switches. If the prover isn't maintained, it can affect the quality of the prove. And another key consideration is variations in conditions at your flow meter and the prover. So if the temperature is different between the meter and the prover, you're going to have different fluid properties, for example, thermal expansion, all that kind of thing. It's always good if possible to allow conditions to stable, because that leads to a much better prove. So I'm going to talk about pipe provers because these are quite a common type of prover used in custody transfer. So what is it? Well, in simple terms, it's a length of pipe, part of whose internal volume has been determined accurately. So you've got the known volume, it's contained between detector switches. There's some form of displacer in the pipe, so it might be a sphere, it might be a piston. As flow moves through the pipe prover, the displacer triggers the first detector switch. That's when you start counting the pulses from your flow measurement device. It triggers the second detector switch. That's when you stop the pulse count. So you get a total number of pulses. You know the calibrated volume. You can work out a K factor or you can determine a meter factor. So I'm not going to talk about every single type of pipe prover, but a good example is a unidirectional ball prover. So this is where you've got a displacer that travels in one direction along the pipe. Now, this displacer is usually an elastomer like a neoprene or polyurethane ball, and it's hollow. And what you do is you inflate this displacer to sort of, 2 to 5% more than the internal diameter of the pipe. Now, why is that important? It's important that the displacer creates a seal between the wall of the pipe because you don't want fluid moving from the upstream to the downstream side. Because that affects obviously the quality of the prove. It's important that the displacer is maintained because if the displacer is of poor quality or it becomes damaged, it will allow flow to pass from the upstream to the downstream as well. So the displacer is usually released into the flow using a special valve. The displacer triggers the first detector switch. You count the pulses, and then when you hit the second detector switch, you stop counting pulses. And you know the volume between the detector switches, and that's how you can determine a meter factor. Now, typically, provers are grouped into two categories. You've got conventional provers, where the volume of the prover has been designed so that you can collect at least 10,000 pulses from your flow meter. Now, why is it important to collect 10,000 pulses? Well, whenever the start and the stop detector switches are triggered, this occurs randomly along the meter pulse train. So when you do that, you're actually missing a fraction of a pulse when you start and stop the switch. Now, if you collect 10,000 pulses, that fractional pulse becomes quite a small proportion of the overall pulse count, so it becomes insignificant. Now, what happens if you've got a prover where the volume's not sufficient to obtain 10,000 pulses? Well, these are termed as compact or small volume provers. Now, to get the resolution required to obtain similar uncertainty to a conventional prover, you need to utilize pulse interpolation. So you need to calculate those fractional pulses. Now, a really common technique is dual chronometry, and this uses two timers. So the first timer times the interval between the detector switches, and the second timer times the interval between the nearest integer of meter pulses. So the first pulse after the start switch and the first whole pulse after the stop switch. By using a ratio of these times, you can work out an interpolated pulse count. Now, the advantage of compact provers is they're used when space is limited, so they've got a much smaller footprint than conventional provers. So there are ISO standards that go into more detail about pulse interpolation. So ISO 7278 Part 3 talks about all the various pulse interpolation techniques. It's typically handled by a dedicated flow computer, and it's important to note as well that even with conventional provers, there might still be an issue with collecting 10,000 pulses if the meter that you're trying to prove outputs a particularly low frequency. So pulse interpolation can still be used with quite large provers as well. I'm just going to finish this section on master meters. So although they're not provers, they can be used to prove a flow meter. So they act as a transfer standard between a meter in the field and another prover or say a calibration facility. So by running the master meter in series with your duty meter, you can make the comparison. It's obviously not as accurate as direct proving, but it does have its advantages. It's usually master meters a lot more compact. So if you've got an installation where it's not practical to, deliver a full-size prover on the back of a truck, for example, master meter is going to be a much more compact solution. Key considerations with any master meter are it needs to be reliable and repeatable, so it needs to have been calibrated or proved at a traceable calibration facility, for example. A good example of master meter use is positive displacement meters. So they've been used for years to verify petrol pumps. We talked about PD meters being very reliable, repeatable. They're not sensitive to installation effects, so that makes them ideal to be used as master meters. I'm now going to talk about fluid sampling. So why is sampling important in custody transfer metering? Well, we talked about gross standard volume, but most crude oil systems you need to report net standard volume because no one wants to pay for seawater, no one wants to pay for sediment. They're interested in the valuable fluid. So sampling is really critical to verify the quality and the quantity of the product that's changing hands. Now, whenever you take a sample, there's several key considerations. First is the flow must remain mixed. So if you've got oil and water in your system, they have a tendency to separate out. The water sits in the bottom of the pipe, the oil sits in the top. Now, if you sample from the top of the pipe, you're just going to be drawing off oil. So whenever you take a sample, you need to ensure that the fluid remains mixed. It's important that the flow remains representative and stable throughout the sampling period. A really important point is the sample that you analyze must be the same as that which you've taken from your flow stream. So that's where sort of proper sample handling comes into the fold. So if you take a sample and it's improperly handled, let's say the sample contains volatile components and the sampling container is not suitable, these volatile components can evaporate off, and when it comes to actually analyzing the sample, the composition is changed. And again, when it comes to analysis of a sample, you usually take a smaller subdivision of the sample as a whole. You need to, at all points, make sure that the composition is the same as the original sample. So what are some mixing methods? So obviously you need to make sure the fluid is mixed. Well, common techniques are using static mixers, and static mixers provide distribution and dispersion of the flow. Some of them have one stage, some of them have multi-stage devices, or you can use things like a jet mixer where you've got a dedicated jet mixing pump. The advantage of a jet mixer is usually you're bypassing the flow, so you're not introducing a pressure drop into the line. So both have their pros and cons. One thing that is important when you select a mixing technology is you don't want to form an emulsion, because if you form an emulsion between oil and water, it's not going to separate out, and that can cause you all sorts of difficulties down the line. Composite sampling is again really important. So this is where a sample is composed of a number of smaller samples taken over time or flow intervals. So obviously in a metering system, conditions are not going to be fixed at one flow rate for the entire time. Conditions will change, temperatures and pressures will change. In order to have a sample that's representative of these sort of changing conditions, you need to use composite sampling. So there's different techniques. You can use time proportional, where you collect samples at a defined time interval. Flow proportional is more common, and this is where the samples are taken at a rate which is proportional to the rate of the flow of your liquid in the pipeline. So you've usually got some kind of flow meter or flow measurement device that is setting the pace of the sampling system. And in terms of types of sampling system, you can get inline installations that take the sample directly from the main flow stream, or you can get bypass or fast loop systems that will quickly bypass the flow and then take a sample in that way. There's pros and cons to each of these, and obviously sampling as a topic, there's more in terms of details that I can go into in the sort of short 4 slides that I've got here. But there are comprehensive ISO standards out there for sampling of petroleum products. So ISO 3170 details manual sampling, and 3171 details automatic pipeline sampling. So 3171 is quite a robust standard. So if you want to learn more about sampling and the different considerations, then I would consult these documents. So I'm moving on to the final section where I'm going to talk about secondary instrumentation and flow computers. So we've obviously discussed flow measurement, but in addition to flow measurement, there's various other measurements that you need to take in a custody transfer system. So temperature and pressure measurement are really important for determining things like fluid properties. Density measurement can be important depending on the metering technology you've selected in order to determine the mass of the fluid. Differential pressure again is critical, especially if you've selected a differential pressure flow meter. You need to measure the differential pressure. You've got various different transmitters and communication types, and flow computers again are another critical component. So I'm going to talk a little bit about each of these just to finish off the webinar. So density determination. Why would you want to characterize the density of your fluid? Now, in relation to liquid systems, especially in the North Sea, many still make use of volumetric flow meters. So if you've got a volumetric flow meter, but you need to know the mass of your fluid, how do you get from mass from volume? Well, you need to know the density. It's especially important for allocation because this is typically done by mass. So in order to get mass, you're going to need some form of density measurement unless you're using like a Coriolis meter, which will give you the mass directly. Now, the most common used technique is a vibrating tube densitometer, and these are very good devices provided that you've installed them correctly and calibrated them properly. So how does a vibrating tube densitometer work? Well, it's very similar to the way the Coriolis meter measures density. You've got a vibrating test section that contains your fluid, and as the liquid density changes, this changes the total vibrating mass. And how do you detect that? Well, you can detect it by a change in the resonant frequency. So you measure the frequency. Now, the frequency depends on not only the mass, but the stiffness of the measuring tube. Now, the stiffness depends on constants that usually are provided by the manufacturer, or you can get them through calibration. And then you use that with the oscillation period, which is just the inverse of the frequency, to calculate the density of the fluid at a measured temperature and pressure. So to put it simply, denser fluids will vibrate at a different frequency than less dense fluids. So by measuring the frequency, you can determine the density of your fluid. Now, what are the advantages and disadvantages of this type of device? Well, they're relatively simple and easily automated. They can be used over a wide temperature and pressure range, and they can be used in line. Now, they're quite a mature technology as well, so they are commercially available and they're potentially very accurate. So you can achieve as good as plus or minus 0.02% uncertainty on density measurement, provided you calibrate them. So downsides are they can be expensive to purchase, and in order to meet that kind of uncertainty, careful calibration is required. So the image here is actually a densitometer being calibrated at NEL. So we have a liquid densitometer facility where we calibrate densitometers over a wide range of temperatures and pressures. So to meet these uncertainty targets, you really do need to calibrate the device. I'm now going to talk about pressure measurement. Again, why is pressure measurement important? Well, it's critical for determining things like fluid properties. We talked about things like Coriolis meters having a pressure effect. If you want to correct for that, you need to measure the pressure. They're obviously important for safety, but when it comes to dealing with pressure measurement, it's important to be clear on the terminology. So you'll hear absolute static pressure and you'll hear gauge static pressure. So what is the difference between it? Well, absolute pressure is pressure measured relative to a vacuum. Gauge pressure is pressure measured relative to the atmosphere. Now, It's important to know whenever a pressure is stated somewhere, is it the absolute or is it the gauge pressure? Because these terms can be confused. So it's important whenever you see a pressure to determine is it the absolute pressure, is it the gauge pressure? Differential pressure is simply pressure relative to another pressure. So this is quite critical for things like orifice plates, venturi tubes. And we talked about standard pressure. Again, this is key for converting to things like gross standard volume, for example. So again, typically it's 1.01325 bar, but it's not a given. You need to make sure that whenever standard pressure is used for converting quantities, that it's stated somewhere what the standard conditions are. Now, when it comes to pressure measurement, various instruments have been invented to measure pressure with different advantages and disadvantages. So I'm not going to go through every single type of differential pressure measurement device. Really common type of device is a capacitance diaphragm sensor. So this is where you've got a sensing diaphragm between two capacitor plates, and when you apply a pressure to the diaphragm, it reflects in relation to that pressure. By measuring the change in electrical capacitance, you can relate that back to the applied pressure. So depending on what you're measuring, if it's gauge pressure, you might have one side you're applying your pressure, the other side's open to the atmosphere. If it's absolute pressure, so if it's an absolute pressure transmitter, one side might have a vacuum and the other side is your applied pressure. Differential pressure, you've got two ports. So differential pressure, like I mentioned previously, senses the difference in pressure between two ports. And when it comes to differential pressure transmitters, which are typically used in custody transfer systems, if it's an orifice package, for example, you've got your pressure sensing element in the bottom half. That might be your capacitance diaphragm sensor. And you've got your electronics in the top half. And you've got two pressure ports marked high and low. Now, why is differential pressure important? Well, it's often used for the measurement of flow rate in orifice and venturi meters. So these flow meters have the primary element in the orifice plate. It's the plate that's causing the restriction. The secondary element's the differential pressure transmitter. So the performance of an orifice plate is highly dependent on the measurement of differential pressure. So it's important that whatever you select, what method you use to measure differential pressure, that again you're measuring it to a low uncertainty. Temperature measurement is another critical component. Again, it's really important for calculating things like fluid properties. It's also important for accounting for things like thermal expansion. So again, orifice metering, it's quite important you get the dimensions of the orifice plate measured to a low uncertainty, but changes in temperature will cause thermal expansion on the pipe. So how do you account for that? Well, you need to measure the temperature. There's different methods for temperature measurement. I'm just going to focus on resistance temperature detectors in this webinar. So how does a resistance temperature detector work? Well, it works by measuring changes in electrical resistance of some form of metal element. So usually platinum is the most popular material, but it can be nickel or copper. Why is platinum so popular? Well, it's fairly stable, and more importantly, the resistance to temperature relationship is fairly linear. So you can characterize that relatively easily. So by measuring the resistance of the element, you can then relate that to temperature. Now these come in different wiring configurations. You get 2-wire, 3-wire, 4-wire devices. I won't go into the details, but 4-wire typically is the best choice because it eliminates the resistance of the measuring lead. So if you think you've obviously got 4 wires that are required to measure the resistance. If you're using a 2-wire system, for example, and you have a particularly long length of cable, by the time it gets to your control device, the resistance that you're going to measure includes that cable length. Now that can be quite significant, but with a 4-wire system that's eliminated. So 4 wires is usually the best choice. They also come in different types. So you've got PT100 RTDs. That just basically means if you measure 100 ohms, that it should be at a temperature of 0 degrees Celsius. But you also get PT25 and PT1000 are another sort of common type of RTD. Now, whether it's pressure, temperature, or even density, whatever you're measuring, there's usually some form of transmitter connected to the sensor. So what is the job of the transmitter? Well, it's taking the measurement from the sensor, so if it's a capacitance diaphragm pressure device, it's taking that and it's isolating, amplifying, and filtering out any electrical noise. But usually the most important thing it's doing is it's converting the input signal from that sensor to a standardized output. So it's taking that capacitance or it's taking that 4-wire resistance measurement and it's converting it to some other output signal. Now, commonly, things like 4 to 20 milliamp, 0 to 10 volts have been used, but digital signals are also popular now as well. So they've all got their advantages and disadvantages. Digital communication protocols tend to be able to give you more diagnostic information. Digital instruments, typically the upfront cost is more expensive. And 4 to 20 milliamp is still widely used. It's not going anywhere. So again, I'm not going into too much detail here, but there's advantages and disadvantages to each type of comms protocol. I'm just going to quickly finish on flow computers. So these are a really critical part of custody transfer metering. And what they do is they implement the required algorithms using all the various analog and digital signals received from your flow meters, your temperature, your pressure instrumentation, your density devices, and it will do things like convert into base conditions amongst other calculations. So as a typical example, the flow computer might take in the pulse train from your flow meters, take in 4-wire resistance, might record raw pressure from a transmitter in milliamp, might take in density, takes all these signals, converts them. So if you've got 4 to 20 milliamp for your pressure, it will convert that into a pressure measurement for you. It will store key parameters like meter factors from your proofs. It'll perform various calculations. So for example, ISO 5167 discharge coefficient or AGA8, natural gas calculations. The flow computer typically is going to do that for you. And more importantly, it's going to convert actual to standard volume. So if you need to report gross standard volume, the flow computer is usually going to do that for you. What's really important is the flow computer needs to be audited on a regular basis because you could spend all the money in the world in a really sophisticated metering system, but if there's an error in the flow computer, someone enters something incorrectly, it's going to mess up the measurement results. So it's important these are audited and checked on a regular basis. So we've come to the end. Just a quick summary. Custody transfer is defined as a metering point, or custody transfer metering is defined as a metering point where the fluid is being measured for sale. So it's acting as the cash register. Requires a low uncertainty, typically 1% on gas and 0.25 with liquid. And to meter to this uncertainty, you require a full sort of comprehensive system that includes flow meters, provers, density, temperature, pressure, sampling, and flow computers as well. So